Alright guys, I'm Eric, and today we're going to redo the lecture portion from the very beginning. I'm going to try to incorporate all the different things that I've learned along the way about how to engage you guys and appeal to the specific audience I'm working with. And so I picked a new topic, and today we're going to learn about thermal expansion coefficient, which is a big mumbo jumbo. We'll talk about what it is, why it's important, examples in your everyday life, and we'll get to see a little demonstration. So I guess first off is, who knows what heat is, or what temperature of something is or means?
It's a type of energy.
Yeah, it's a type of energy, right? So the idea is that what temperature really is a measure of how fast are little molecules inside of a solid or liquid or gas jiggling back and forth. So if you heat them up, and they start moving faster and faster, bouncing into each other, as they bounce harder and harder, they'll want to end up further apart. So the idea is that whenever you heat something up, it will actually get bigger. It will expand in most cases. And so we have a way to write this down, which is, it looks complicated, but it's really just a sentence in equation form. So what we have is a change in length equal to the initial length of some object, this thing called alpha, which is the thermal expansion coefficient, and then a change in temperature, right? And so this alpha is unique for each individual material, and it's just a number you look up. So even though it looks complicated, all the sentence is saying that we know that if you have an object and you change its temperature, its length will change. And depending on what object it is, depends on by how much. And so we can make it even simpler, is this delta L, if we divide this L onto the other side, well, you could say, what if delta L was a tenth of L, or a hundredth of L? You'd have an L on the top and the bottom, and those would divide out. And so what we can look at instead is just this ratio, which is just the percent change. So this way we could say, this whole number could be 1%. We could ask the question, how much of a temperature change would you have to increase the length by 1% for a given material, or something like that. So to give us an order of magnitude, an estimate, I'll use steel, where the alpha ends up being about 20 times 10 to the minus 6. So pretty small, right? So that means that even if I change the temperature by 100 degrees, that'll go from 2e minus 5 to 2e minus 3, so 0.2%. Right? So even a 100-degree change only changes the length of the thing by 0.2%. That doesn't sound like a lot, and it doesn't seem like something that we'd see in our everyday lives or really care about. So one fun example is, I lived in an apartment with a terrible old air conditioning system. And one time it stopped working, so I took the little cover off and looked at it to see if I could figure it out. And it was kind of interesting because inside what I saw was this. It had an enormously spooled length of copper string, little copper rectangle, and was attached to a little vial that had mercury in it. And so literally as I turned the thermostat, it would move the very tip of this, so that whenever the temperature changed, this thing would get longer or shorter, and would push the vial up or down. And as soon as the vial tipped, the mercury would flow to the other side. If it tipped back, it would flow down to one side, and there were two electric leads. So literally, it was this thing expanding, pushing mercury into making these two contacts connect and completing the circuit. Super simple. Today we don't even know we have computer chips and stuff like that. But the other trick is we had to have this huge coil because it needed such a huge length for it to make any significant difference. So why do we care about that? Well, it turns out that usually that's not the situation we care about. What we care about is instead, what if you have two materials and they're joined together? Say this one's copper and this one's iron. So if I change the temperature, these are both going to have different thermal expansion coefficients, which means they're going to change a different amount of length. So if one gets longer than the other does, what's going to happen? Exactly. So initially it had to look like this. We had some kind of 90-degree angle. The only way to conserve that would be if they both bent to try to conserve that angle. And now the one on the outside has gone further than the one on the inside, because the inside is a smaller circle, the outside is a bigger circle. And so they get to match. Eventually this will stop working, right? Eventually they have to break, something has to give. But this works for a lot. And this is the kind of thing where you can magnify the effect and start to see it actually affect things. So I'm going to show an example of exactly that system. So usually you're supposed to wear the safety equipment, but we're all friends here. So, I already heard it, but who knows what this is?
Dry ice.
Close.
I don't know.
This is, dry ice is a solid, that's solid carbon dioxide. This is liquid nitrogen. Anyone know what temperature this liquid nitrogen is at? So, it's going to see here it's boiling. It's trying to get the glass itself to about the same temperature, and then it'll settle down. So this is at about negative 200 degrees Celsius, which is the same as about negative 350 degrees Fahrenheit. So it's cold. So we'll wait for it to settle down. It'll get nice and quiet. You can listen and hear. So does anyone know how much of the air? Over here, we're listening right now. All right. Does anyone know how much of the air is nitrogen? About 80%. So we're already breathing this all the time anyways, which is the fun breathing gag. So we've seen now it's quieted down. Everything's about the same temperature. And I've got here a bimetallic strip. Pretty thin, pretty straight. On one side copper and one side iron. And we're going to dip in here for a little bit and see what happens. See how much of an angle this really makes. What kind of a difference does it have? And will we expect to see this in our everyday life? Obviously with negative 350 degrees Fahrenheit, not exactly, but it gives us an idea of what's happening at a molecular level. It's only been about 10 seconds. That's probably good enough.
Wow. Wow.
So this is what starts to matter when you're designing a bridge.
Oh.
Right?
Why?
If you try to construct a straight bridge and then this happens whenever it freezes, and it is thicker than, a millimeter or two, this is going to start to break and crack and destroy iron, concrete, anything that you have, this is going to break. So, have you guys ever tried to take a dish out of the dishwasher and then maybe run it under cold water because you're not a very smart person like me? I have. You know what happens when you do that? It cracks, it breaks. That is this happening again. Right? So this is again where you are seeing these different contractions, these different angles happening, and when your material can't take it anymore, it'll just shatter. So we don't look for it in terms of an actual absolute change in length. We look for it when the temperature changes across material, start to cause differences in contractions, and it'll rupture the material. And there's a last note of interest. Can anyone think of an example? You like that? All right, good. Carry on.
My chemistry teacher did it over the crowd.
So can anyone think of an example where this actually is backwards? Where something doesn't get bigger as it gets hotter? It's actually something we all deal with every day in our everyday lives.
That's what I was thinking,
Sorry.
but I was
Water.
like, how do you say it? Yeah, because I was like,
Ice.
is it ice or is it water?
Right. It's one of the only materials that does that. And between 0 degrees Celsius and 4 degrees Celsius, it actually expands when it gets colder.
Yes.
And that makes it less dense, which means that it can float on water. If that didn't happen, that would mean that every time a layer on a lake froze, it would sink to the bottom. And the next layer would freeze, and it would sink, until the entire lake was completely ice. So if it weren't for the opposite thermal expansion coefficient of water, we probably wouldn't have life on Earth. Because the ice on the top now is able to form an insulation layer and keep all the liquid water underneath. So it turns out that this matters in a whole bunch of different places, from our everyday lives to the whole being of life on the Earth. And we can actually see the effects in a standard material that I got to bring in for a demo. And we got the liquid nitrogen, which is all it says. So.